Part 2 of this video is going to start with the factoring problems. And factoring, we're going to be looking for those patterns. We're going to be looking for greatest common factor. We're going to be looking for difference of perfect squares, difference in sum of perfect cubes. So the first thing I always look for is greatest common factor. Always, always, always I look for that first. In this first example here, x to the fourth minus 81, there are no greatest common factors. After greatest common factors, I look for one of my patterns, perfect cubes or perfect squares. And this problem is in fact a perfect square. If you think about it in this way, you can see we have the difference of perfect squares. Difference of perfect squares always factor into the square root of the first thing minus the square root of the second times the square root of the first thing plus the square root of the second. Since we started with a power higher than 2, we always have to take a look to make sure that this subtraction part doesn't become another perfect square, which in this case it does. So I can take x plus 3 times x minus 3 for this first part. I can't factor this, and so I have this as my final answer. Everything is completely reduced and factored out. Now in this next example, greatest common factor first, I see a 3 as a factor for each one of these. So I'm going to take that 3 out, and when I take it out, it's division. And so I end up with something like this. So then I can very easily, my 3 is going to stay out front, I have plus plus, and I can think about what factors of 15 will combine under addition to make 8. Well, clearly, if you make your list 1 times 15 and 3 times 5, you see it has to be plus 3 and plus 5. Now, the order of those two doesn't matter as long as they're in the back. So that's a nice, easy one. 21 and 35 have a common factor of 7. X cubed and x have a common factor of x, and when I take that out by division, I end up with something like this. There are no common factors or factor pattern in 3x squared minus 5, so I know I'm done. Okay, so when I look at this next problem, I need to check for greatest common factor, which obviously there isn't, and then I check to see if it matches any of my patterns. Because it's 2 terms subtracted and I see this cube, it makes me wonder, can I write 64 as a perfect cube? Well, if you check your cheat sheet, you see you can. So this really, on your cheat sheet, is this pattern. Well, what is the rule for doing that? The rule says take the base of the first 2 and subtract them. So my bases are those. Then it says take the base and square it, add the 2 base multiplied, and then add the second base squared. So in this case, W was my A, 4 was my B, and I just go ahead and follow the pattern. Then you're going to want to go ahead and clean it up. And really the only cleanup you have to do is at the end here. And that is how you factor the sum or difference of perfect cubes. It's just a matter of following that pattern. Now simplifying with roots, a couple different ways always to go about things. So I'm going to go ahead and factor this. This time I'm looking for powers of 4. So anything that ends in 5, I know that 5 goes into. And I know that 5 goes into 125. And I know that this factors like this. So I know that I have 2, 3, 4 factors of 5. So remember, we're going to rewrite this as 5 to the 4th, and I'm going to take that b to the 7th. I can make one group of 4 and then my leftover 3. So I come back, what's the 4th root of 5 to the 4th? That's 5. What's the 4th root of b to the 4th? That's b. Can I take the 4th root of b cubed? Nope. So that's my leftovers. And that's my final answer, as simplified as it can go. So now here I've got a power of 4 when I am squaring. So remember what that means. That means that I have the square root of x minus y squared. So what's the square root of something squared? It's just the something. And so that is your final answer. The other way you could think about this problem is you could think about this as a fraction, and you could have x minus y to the 4 halves, which reduces to x minus y, still in the parentheses, squared. So you see you get the same answer no matter which rule you apply, as long as you apply the rules correctly. Now, this problem, there's no plus in between. This is a FOIL problem. So go ahead and take your first two terms times each other, outside terms times each other. Remember, coefficients times radicals, multiply like that. Inside terms plus 4 times the square root of 3, and your last two terms. Now, I'm not necessarily going to go ahead and multiply these together. I'm going to write it like that because we know we're going to have to simplify. Nothing can be simplified in the first part, but 15 is 3 times 5. So that means I have two factors of 3 and a factor of 5. So I have 12 minus 3 square roots of 15 plus 4 square roots of 3 minus the square root of 3 squared is 3 with a leftover of 5. Because none of those radicals are identical, I cannot combine them, and that's your final answer. Now, I have negative 64 under the cube root. Remember, I can take odd roots of negative numbers. So what is this? This is 3 to the negative 4 cubed. What's the cube root of something cubed? Just the something. So there's your answer. Now here I have a straight up addition, kind of subtraction, mixed problem, but all of these radicals need to be reduced before I can do anything. So I know 20 is 4 times 5, I know 24 is 4 times 6, 18, well let's see, that's 18 times 10, which is a factor of 9 and 2, and 2 and 5, so there are my perfect squares, and 54 is a factor of 9 times 6. Now you notice I didn't factor these all the way down this time because I know when I hit a perfect square like 4, I can stop my factoring because I know I can take the square root of that. So what do I have here? I have 5 times the square root of 4 times 5 plus the square root of 4 times 6 plus negative square root of 9 times 2 squared times 5 plus 7 times the square root of 9 times 6. So then I'm going to go ahead and I'm going to take these square roots where I can. So I'm going to have 5 times the square root of 4 is 2 with the square root of 5 left over. Plus, I can take the square root of 4, which is 2, with the square root of 6 left over. Here, plus a negative square root of 9 is 3, the square root of 2 squared is 2, and I have the square roots of 5 left over. Plus 7 times the square root of 9 is 3, and I have the square root of 6 left over. Go ahead and clean up those multiplications. I have 10 square roots of 5 plus 2 square roots of 6 plus negative 6 square roots of 5 plus 21 square roots of 6. I'm not done until I check. I've got some combining I can do. I have identical roots. So 10 square roots of 5 minus 6 square roots of 5 leave me 4 square roots of 5. 2 square roots of 6 plus 21 square roots of 6 leave me plus 23 square roots of 6. And that is your final simplified answer. Now this problem over here is our bad math grammar with the square root of 2 in the denominator, and we rationalize the denominator by multiplying by the square root of 2. So my numerator becomes 6 square roots of 2. My denominator is the square root of 4, which is 2. But now I have to check, and I can simplify here. And so my final answer is 3 square roots of 2. A lot of times after you rationalize the denominator, you'll have to go back and factor out, cancel out a common factor. We're going to continue with the rationalizing bit. This time I have this plus here, so I actually have to multiply by the conjugate. Remember, we're going to treat these like single numbers. That conjugate value is the same two numbers with the opposite sign. And then the bottom, in this case, we need to FOIL. And up here, we need to do the distributive property. So this is going to get a distributive property, and this one's going to FOIL. So in the numerator, I have 5 square roots of 6 minus the square root of 18 all over 5 squared minus 5 square roots of 3 plus 5 square roots of 3 minus the square root of 9. When you do first inside, outside, last. Start cleaning things up. 18 is 9 times 2, so I have 5 square roots of 6 minus 3 square roots of 2 all over 25 minus plus cancel minus 3. And so I have 5 square roots of 6 minus 3 square roots of 2 all over 22. Take a quick peek. Do 5, 3, and 22 have anything in common? Nope. That's your final answer. I will continue on with the review problems in part 3.